Hello, wonderful people. Welcome to Cosmology Talks and Cosmology from Home. This is the first of a series of talks on the spectacular new sample of supernovae from the Dark Energy Survey. This talk is about the key cosmology paper and also introduces the data and how the awesome people at DESI have extracted and calibrated it. At Cosmology from Home this year, we will be having an extended themed discussion session on this dataset and the cosmology DESI have done with it. So if you want to join that discussion or even just watch it, you should sign up for Cosmology from Home via the link in the description. The discussion will use this talk and its companion talks, which will be released over the rest of the week as framing. In this talk, we have Tamara Davis, Maria Vincenzi and Dillon Brout to introduce us to the data. I don't think this talk needs much more introduction from me, beyond saying that their supernova sample is a factor of at least 5 bigger than the next largest high redshift sample, so there is a lot of new constraining power there. And just like the new DESI BAO data, it appears to favor some sort of evolving dark energy over lambda CDM. So welcome, Tamara, Maria, and Dillon. Do you want to start by briefly telling us about the data and what you've done with it?
Hi everyone, we're really excited to talk about the final results from the Dark Energy Survey on our supernova cosmology. We've been working on this for ages. I've been doing this for well over 10 years now, and many collaborators have contributed a huge amount to these results. So we're excited to be able to share these with you. To give away the punchline, this is our supernova cosmology results. This is the Hubble diagram that we measured using type 1a supernovae. We found approximately 1,500 new high redshift supernovae, which makes up 80% of the known type 1a supernovae that are of good quality that we can use for cosmology. So it's a step change in the amount of data that we have at high redshift for type 1a supernovae, and it lets us do all sorts of cool cosmology.
So one of the biggest challenges in supernova 1A cosmology, which is what this talk is about, is systematics, sources of systematics. So with this, we really set the new kind of gold standards for systematics in supernova cosmology, and we really kind of improve by order of magnitudes things like calibration, systematics related to intrinsic scatter.
And in the end, with this set of relative distance indicators, we're able to constrain lambda CDM, varying the equation of state of dark energy. And while it's still very early, we are seeing hints that dark energy itself may have some change with time.
Awesome. So if people are thinking of this talk or your paper in 6 months or a year from now, and there are only 2 things they're able to remember, what would you like those 2 things to be?
So the first thing is that DES is really a stepping stone to the next generation of supernova cosmology, and that's because it's been a proving ground for collecting enormous samples of supernovae on a single telescope and in single photometric systems. So what we've been able to do in about 5 years of observing with the dark energy camera is to double the currently available set of high redshift supernovae over the last 20 years. And so that makes this the single largest sample of that kind.
And to emphasize Dylan's point even more, so before that, what people had to do is to get 200 supernovae from one experiment, 200 from the other, 200 from another one, and combine everything together to get a good sized sample of supernova 1A to do cosmology with. But with DES, you can do this with basically one experiment, which makes the measurement, the treatment of systematics much more robust and easier also.
And as a result of all this amazing data, we've found hints that dark energy may vary with time, or the equation of state might vary with time. And although we don't want to jump to any conclusions, we always need to get more data and stuff, it's really quite intriguing that after our results came out, some similar results from the Dark Energy Spectroscopic Instrument also came out using baryon acoustic oscillations that found a very similar result. And so I feel like it's a really intriguing time in cosmology.
We're throwing darts at a dartboard from kilometers away and just missing the bullseye repeatedly, which is, I don't know, maybe the best case scenario, because if you're completely missing the dartboard, you feel like you don't know what you're doing at all. But if you're hitting the bullseye, it's not that interesting.
Yeah. It's also we did all this analysis blinded, which is really important for cosmology. So we didn't look at the cosmology results until we had just finalized all our data and what we thought was the exact best analysis that we could possibly do. And so we weren't biased by what results came out. So we had to be excited by what we found on the other end. Yeah, and we didn't make any changes at all after unblinding to the data.
And I guess you didn't mention this explicitly so far, but the supernova data here is public or will be public very soon. And so if people want to test their own models that aren't W0 and WA, they can do it?
The supernova data are all of these data are all already public. So anyone can download them, and we're trying to make it really easy so people can download it and have some tutorials on exactly how to use the data so that everybody can use these and get the most out of the data that we've provided.
Cool. So if you want to go into a bit more detail into the background and motivation, I think it sort of speaks for itself why it's useful to have a sample of 1,500 supernovae all from one telescope, but there might be other details about why this is interesting. Why was it specifically the Dark Energy survey that was needed to have this? Why couldn't previous telescopes also get 1,500 nice supernovae? And
So I think before kind of diving deep into DES and the results we got, we thought about spending very few slides just reminding how we do supernova 1A cosmology. So we wanted to start kind of from the basics. One of the most direct ways of tracing the expansion of the universe is by measuring how distant an object is and how fast it's recessing from us. Now, measuring distances is quite challenging in astrophysics and cosmology, but there are these tools called type 1A supernovae that are extremely useful for make distance measurements. So supernovae 1A are these thermonuclear explosions of carbon-oxygen white dwarfs, and the interesting properties about supernovae 1A if they have this remarkably homogeneous peak brightness. So in these slides, we just show a supernova popping up in a galaxy and the light evolution, also called light curve, of the supernova. And the peak brightness of that supernova is so homogeneous across many supernovae observed in the universe that we can use that as so-called standardizable candles. Why we say standardizable candles? Well, because the brightness of the supernova alone is not as homogeneous as we would like to make a precise cosmological measurement. So what we do is we study the properties of the supernova light curve, for example, its stretch, which we call usually x1, its color, which we call T in that equation, which host the supernova is based at. And in this way, we kind of can correct and homogenize further the intrinsic brightness of supernovae and get a very precise, less than 10% uncertainty distance measurement. So that gives us the distance part. The second information, as I was saying, we need is the recessional velocity, which in cosmology we call redshift. And that's actually the easy part, because thanks to the Doppler effect, we can look at the host galaxy where the supernova exploded and get a very accurate measurement of how redshifted the galaxy and the supernova itself are. So then if we put this information together, distance and redshift, we can directly trace the expansion of the universe. And in the relationship between distance and redshift is encoded the cosmological model of our universe. And here we put kind of the two most important equations you need to know if you want to connect this distance and the cosmological model of your universe, and how we actually link the distances to this quantity mu, this called distance modulus, that is just kind of the logarithm of this distance. So by comparing distance and redshift, we can determine whether our universe is decelerating or accelerating, and what is the main ingredients and the content of our universe. This measurement was done for the first time 25 years ago, and we indeed discovered that the universe is accelerating and is dominated by dark energy. And these are the kind of contours that, assuming dark energy is just a constant, you will kind of see omega matter, cosmological constant omega lambda. But usually, actually, nowadays in supernova 1A cosmology papers, you would see that we test expansion of the so-called lambda CDM model. So what we can do is to introduce an extra free parameter called W that basically parameterizes the equation of state of dark energy, and you can test whether the hypothesis of cosmological constant is correct or not. Or you can further kind of add an extra degree of freedom in your equation of state of the dark energy and use so-called W0 WA CDM kind of model that just linearly expand the equation of state parameter W. So basically, all this information about which cosmological model you're trying to test are encoded in this like integral in the definition of the distance, luminosity distance that you measure from supernovae. And so this slide summarizes all the plots you will see in this talk a Hubble diagram, this distance redshift diagram, and these contours that sometimes will have omega matter, W, W naught, WA, and they all just describe different cosmological models. This technique of tracing the expansion of the universe using distances and redshift started actually 100 years ago when Hubble, without not using supernovae 1A but using Cepheids, found out that our universe was indeed expanding. It took us 70 years to kind of push the diagram that Hubble made in 1927 at even farther distances and higher redshift. And using supernovae 1A 25 years ago, we discovered that not only our universe is expanding, but this expansion is accelerating. And that measurement back then was done with less than 60 supernovae. And now this brings us to 2024 with Dark Energy Survey that managed to increase that number by almost 2 orders of magnitudes to 1800s.
One thing I find interesting about the 98-99 discovery was they were measuring the deceleration parameter. It makes it sound like it was an overwhelming surprise that it was accelerating. There were already people speculating that it was accelerating. But I don't know, I just find it funny that they measured the deceleration parameter and it turned out to be negative. Shows kind of how prior expectations might bias you a little bit if you're measuring the deceleration parameter.
Yeah, and it was really interesting actually in the original one, it is talked about as a big surprise that there was dark energy there, but the age of the universe was wrong, the number counts of galaxies at high redshift was wrong, the matter density was not 1 if you just measured the galaxies. So it landed on fertile ground, which is one of the reasons it was accepted so quickly. And so it's interesting to look at that in the context of what's happening today. And there's all of these little tensions that are appearing in the standard model of cosmology, and do they need a deeper explanation? So it's in some ways a similar context that our results are sitting in right now.
Yeah, although I guess one of the main differences and why this was kind of like in 99 so immediately kind of accepted is that there was a model that pre-existed that fitted all the data at the time. It was the cosmological constant. I mean, okay, maybe we're now realizing in 2024, 25 years later that the cosmological constant doesn't fit today's data, but it fit the data with the precision they had back then. So our current situation, you know, the Hubble tension's now been around for more than a decade, and there's still no super well motivated new physics model that can just explain that without ruining other things. So we really aren't in a situation now where there is just some clear and obvious model that puts everything together the way that there was back in 1999, which is very curious.
Yeah, absolutely.
With this foundation sample, I presume the supernovae weren't glowing anymore when the Dark Energy Survey was running. But do you use this sample at all when you talk about the Dark Energy Survey constraints? Because that kind of weakens your bold claim that, you know, all of the supernovae come from the one telescope.
No, this low redshift supernovae that you see in orange in that diagram are coming from completely different surveys and completely different telescopes. Foundations were done with the Pan-STARRS telescopes, and there are also some supernovae from CSP and CFA supernova surveys. So to make a good cosmological measurement with supernovae 1A, you always want to have the largest possible redshift range to kind of probe the expansion across a long window of time. The problem is that the high redshift and the low redshift require kind of almost completely different observing strategy. To go very high in redshift, you need to drill down on a very small patch of the sky to get a good number of low redshift supernovae. Because of how the supernova rates work, you want to cover a very large area of the sky and not incredibly high depth. So that's why also, like in 1999, it was the case that 2 different teams with 2 different telescopes, 2 different surveys got the low redshift and high redshift supernova samples, and we're still doing that nowadays. Now, there are ways, and Dillon can talk to you about that, of reusing the same camera, the same telescope, just a new kind of observing strategy to collect a low redshift sample. You just need to cover a larger area of the sky with a lower depth. And this is actually what Dillon and a team of Dillon's collaborators started doing after DESI was done.
So that's the context. Now, how did we get there? So the Dark Energy Survey has been going basically for 20 years. People have took like a long time to design and build the actual camera that went on the telescope. And at the bottom, this is the field of view of the camera. And it's a huge field of view. You can fit a lot of moons across that field of view. And what we did was went and observed this patch of sky that sort of looks like a tank there, which covered really the places where the galaxy and dust is not in the way, and some really commonly observed fields. Now, we observed the whole thing 10 times, but those little circles that you're looking at, we deep drilled and went back week after week to the same fields, and we looked for stuff that changed. And that's how we discovered the supernovae.
So all the supernovae were discovered in these tiny little circle lines of sight.
Yeah, so there's 10 fields grouped in 4 groups. And this is sort of a little animation of the discovery of those over time. And each of those dots is a supernova popping up. Now, you'll notice that when we just observe the supernovae, we have distance information, but we haven't got the redshift information yet. And so what we did was we followed up each of our supernova discoveries with spectra, but not of the supernova itself necessarily. We went and looked afterwards at the host galaxy. And we want to do the host galaxy because it's the one that has more precise lines. And so for that, we used a whole bunch of telescopes, but sort of our workhorse was the DESI survey that we did in Australia. And very conveniently, the Anglo-Australian telescope has exactly the same field of view as the CTIO 4-meter telescope that we used in Chile for the photometry for DES. And so it's an optical fiber spectrograph. It has 400 optical fibers. And so we can take hundreds of spectra at once. And that's the way that we efficiently followed up the supernovae and got their host galaxy spectra. And as a result, we were able to make animations like this, where we are sitting at the very center of this. And these are the 4 sort of main directions that we're looking out at. And as you watch the animation, you'll see these sparkles show up. Those sparkles are the supernovae that we're finding in these pencil beams. Each orange dot is a galaxy, and the sparkles are supernovae, and you see them popping up at the times they popped up. So this is the first 3 years of the survey. You see it for a while, it will stop flashing, and that's because our fields have gone behind the sun. We only observe for 6 months a year. I think this is a really cool demonstration of what we're actually looking at. And this was thanks to Sam Hinton that made this animation.
Is there any ambiguity about what the host galaxy is? I guess all you can see is the line of sight where it is. How do you know that it's not the galaxy in front or behind?
There is some ambiguity about which host it is, and that was one of the systematics that we studied. And so we looked in detail because sometimes it's a bit confusing about which one is exactly the host. So we took all of that into account in the analysis.
It surprises me how many supernovae you're getting from such tiny pencil beams. So I guess there's hundreds of thousands of supernovae obviously actually going off in our sky then. Is there any super futuristic experiment that is actually going to be able to detect all the supernovae going off at that high redshift?
So it's a type 1a supernova estimated to happen roughly once every 100 years in every galaxy. So if you cover enough galaxies, and that means go deep enough or cover enough area, you'll see lots of supernovae. The Dark Energy Survey is just 27 square degrees on the sky, so those 10 pinhole sort of views that you saw there. And the sort of futuristic vision is right around the corner. LSST is going to basically get the whole southern sky with a relatively good cadence. Not quite as good as the Dark Energy Survey, but we think it'll be good enough to do supernova cosmology, certainly. And that's just going to just give us orders of magnitude more supernovae, which, that's why we say sort of this is a proving grounds for that. But we are super excited by that as well.
Are you talking hundreds of thousands of supernovae, or?
Yes, yeah. So from 1800 or so to hopefully hundreds of thousands. Maybe we'll have discovered 1 million. How many of those will be viable for cosmology remains up for question, but we will certainly get to pick and choose the best ones, which will be important when we're in the realm of systematic uncertainties.
And at that point, does spectroscopic follow-up become not so feasible for 100,000 things?
Yeah, spectroscopic follow-up will be the biggest challenge, and that's why as we will explain in a minute, we think DES really is marking a very important milestone for supernova in cosmology, because we demonstrated that we might not need as much spectroscopic resources as we thought we might have needed, and also because for LSST we don't have a AAT that is conveniently located in the right hemisphere and at the same field of view as the LSST camera as we had for that. So that's 2 points that make things a bit trickier.
To give you a bit of context for this diagram as well, if you look at where it sort of the brightness fades off, and there's only a few points after that, that's about a redshift of 1. So beyond that, that's where the O2 line drops out of our spectrograph, and it's hard to get redshifts for galaxies higher than that. So you mostly get AGN after that. But if you're at a redshift of 1, you're looking back half the age of the universe at that point, approximately. And so you're looking, even though it's a narrow pencil beam, it's a huge volume, actually. So there's a huge number of galaxies in there, which is why we are so efficient at finding supernovae. And it's because the end of the cone is bigger, the further away you go. That's why it's easier to detect high redshift supernovae than low redshift supernovae, because the point of the narrow end of this cone is just so small. There's just not enough galaxies that you're going to be likely to find supernovae in the ones that are just in the near end of the cone. So as a result of all that, we measured some supernovae. So here is a plot of the number of supernovae as a function of redshift from previous surveys. So the gray colors that you're seeing here are the Pantheon and Union compilations, which combine 17 historical surveys. The blue line is the 3-year DES sample that was just our spectroscopically classified, where we got spectra of each of the supernovae as well as the host galaxies. And our new sample looks like this. So the blue is our new sample, and you can see just how many we get at high redshift compared to what existed before. So that's why it's a bit of a step change in data. And the other thing that you'll notice is we do combine with the low redshift samples, but what we do is we only choose the most homogeneous, well-calibrated low redshift samples to add to our high redshift data. So we actually throw out more than 2/3 of the low redshift existing sample so that we only get the absolute best quality ones, so we can control the systematic uncertainties as well as we possibly can. Because the entire focus of this from start to finish with the Dark Energy Survey was to be able to control our systematic uncertainties, and calibration is a big one there. So we could have had tighter constraints if we'd included all of those existing supernovae, but we went for quality over quantity and got rid of some of those low redshift ones.
Is there any concern about selection effects there, that like the ones that you're choosing to remove might be somehow correlated with something cosmological or anything like that?
I would also emphasize one of the reasons why some of those were rejected at low redshift is because we couldn't model the selection from those individual samples. So these that we've used are the ones that we can model from these sort of follow-up surveys that have very dedicated strategies that we can model in simulations. So I would say perhaps it's the converse of that.
For our sample, what we classified all the supernovae photometrically, so based on their light curves, and that we'll see that in a second as well. And that has a big advantage over requiring a spectroscopic, like a spectrum of each supernova itself, because the follow-up to get those spectra is really hard to model your selection effects for, because it's like, did I have telescope time on that night, on the night when it was bright, and that kind of thing. So having a photometrically classified sample actually makes your selection effects a lot simpler. So it's quite nice. So these are our light curves. And this is, I think, the favorite plot that I've ever made. I like, just looks very colorful. But this is, we had 4 bands, so we measured in 4 colors for each of our supernovae. So here you see the G, R, I, and Z band colors, and each of the supernovae will appear in each of these bands if we have data for them in that band. What I've done is I've offset them by redshift. So as you go up in the diagram, I've just artificially offset all of the light curves by their redshift. So the highest redshift ones are at the top. And you'll notice that as we go to higher redshifts, the supernovae aren't bright in the blue anymore because that blue has been moved into redder passbands. So that's why we don't have G-band data for the high redshift ones. And so you can see that the G-band drops out around redshift 0.35, and then the R-band drops out at about redshift 0.85. So this is actually, I love looking at data. This is what our data actually look like. And that's what ends up going onto our Hubble diagram. So each of these blue dots comes from one of the light curves here.
Why DES could go so much deeper than previous surveys? And the key point is that previous surveys that have been included in Pantheon Plus, Union, have been much more focused on selecting supernovae 1A, for which the type has been determined like very accurately, mainly using spectroscopic data on which you can see the particular features that only a type 1A would have. Now, requiring external spectroscopic data of the transit of the supernova itself is something that introduces significant selection effects, because external spectroscopic data are extremely more limited and expensive to obtain, and they introduce selection effects that can be tricky to model. With DES, we included all the supernovae for which we had those light curves that the DES camera could observe. And based on the shape of these light curves that you see in these 4 filters, we classify or determine whether a supernova was looking like a 1A or other type of supernovae, usually core collapse, that have shapes that are similar to 1As, but they're not standardizable candles, so shouldn't be used for cosmology. So when we put all our supernova events on a Hubble diagram, that's what we obtain. So again, Hubble diagram is distances versus redshift. Here you can see our low redshift external sample in orange and our beautiful DES sample in blue. And what we put in the bottom panel is the residuals between the DES observed distances and the best fit cosmology we fit through those points. And one thing that people quickly can notice is this population of outliers. These are supernovae that have a light curve shape similar to supernovae 1A, but likely core collapse, so fainter, a population that is fainter than supernovae 1A, and so it looks like this kind of positive outliers, positive Hubble residuals. And as you can see, each of the DES data point is color-coded, and the color coding is precisely the measurement of the probability of each supernova of being a type 1A. And we measure these probabilities using machine learning, and we're going to talk a lot about this. Now, one important note is that the redshift of the supernova is still measured spectroscopically from the identified host galaxy of the supernova. Getting the redshift of a host galaxy, supernova host, is actually much easier in a sense because the host doesn't fade away in a couple of weeks, while supernovae do, and once they're gone, they're gone.
Yeah, what information is given to the machine? I guess so long as you're not giving the information about how good of a fit it is to the WCDM model, then that's a good interpretation. But if you are giving that information, like it might be saying it's an outlier because it's an outlier, and then it's a bit circular. But if you're not giving that information, yeah, that's a very persuasive.
Yeah, that's a very good point. And absolutely, yes, the machine learning algorithm shouldn't know anything about the cosmological information that is embedded in the light curve. So as you will see, we will explain in a couple of slides, but the machine learning algorithm only knows about the shape of the light curve, doesn't even know about the brightness, the signal to noise of the light curves, which are all information that can tell you a little bit about the cosmological kind of how good of a fit to a cosmological model a data point is. So we're extremely careful about that. Yeah.
So when it comes to the analysis, of course, the first step is to build the data set, to calibrate the images, to perform photometric measurements. And by photometric, we mean, counting photons. And of course, getting the redshifts as we've spoken about. But there are a number of other aspects that we've already hinted at. Number two, we need to be able to simulate our data set. We want to simulate it for testing our analysis pipelines, but also for understanding potential biases in our observed data set. We want to classify the data set, specifically looking for these type 1a supernovae, as Maria will be talking about shortly. And we want to model the properties of the supernovae themselves, where they explode in their galaxies, what their environments are like, what potentially the progenitors of these explosions are, and so on. So let's just, if we can, dive relatively quickly in detail into a number of these aspects. So when it comes to building the data set itself of photometric light curve measurements, this is led by Bruno Sanchez. And what we do is model the scene of the galaxy and the supernova itself in a forward modeling process. This encompasses our information about the various effects that impact the images, like the telescope properties, the atmospheric properties, and so on. In doing this forward modeling process, which you can compare, for example, the left is our set of images, on the right is our model. We can constrain very well a model for the supernova as a function of time, and constrain its photometry to less than about 0.5% or 5 millimags. One of the big steps that we've taken forward in this aspect in preparations for what's coming in the next generation of supernova cosmology, and this effect, which you can see here, is being greatly exaggerated, but what we do account for is atmospheric effects, like differential chromatic refraction that changes the inferred position of the supernova and host galaxy on the sky as it's dependent on the source color or the source spectrum. And we also account for changes in the seeing, or basically the blurring or point spread function of the images as a function of the source color. Fortunately for supernova cosmology, we can do this because we have a very well-defined spectral model for the type 1a supernovae, so we can model all of this in simulations. And that's what Jason and Maria have done, Maria Acevedo.
Yeah, and the second aspect we want to talk about a little bit more in details is simulations, which means we needed to build a sample of simulated light curves that had the same properties and observational noise as the real DESI light curves. And this was really important to train the machine learning classifiers and teach them to identify supernovae 1a in the DESI sample, to model our selection effects, to validate our pipeline, as Dillon was mentioning. So the first step of building these simulations was to basically consider the same volume of the universe that is probed by DESI and populated with supernovae, both type 1as, but also all these supernova contaminants. So supernovae that look like type 1as, but are actually core collapse, peculiar 1as, etc. After that, what we did in our simulations is to associate each simulated supernova to a host galaxy, again using realistic galaxy catalogs and knowing the supernova rates as a function of each galaxy property. And then third, we need to apply the observational noise introduced both by the DESI imaging survey that helped us finding the supernovae, but also the additional selection introduced by the OSDES survey that was getting the redshift from the host galaxies. These simulations were really a monumental effort of combining all our astrophysical knowledge about supernova 1a and their host, and the characterization and modeling of the surveys, DESI and OSDES. And now the kind of ultimate test to verify whether the simulations are accurate or not is to compare simulated data with the real data, the DESI data. And one thing I really want to emphasize is that while we were building these simulations, at any point we were kind of fudging or adjusting the input or the assumptions in our simulations to make the agreement with data look good, because that would have kind of defeated the purpose of this exercise of going from first principle to kind of the real data. And here I wanted to show some comparison between the distributions observed, the observed distributions of, for example, redshift, the host galaxy brightnesses, and the so-called Hubble residuals, the ones that we're showing below our Hubble diagram. And these are the observed distributions. And when we overlay these observed distributions with our simulated supernovae, 1As and non-1As, we see that the agreement is remarkably good. So we well reproduce how our number of supernovae at high redshifts are dropping because of all the selection effects introduced by the camera and OSDES. We well reproduce how bright the host galaxy of the supernovae were, and so which ones we got the redshift for and which ones we couldn't. And we very well reproduce this kind of population of outliers as positive Hubble residuals that I was highlighting a few slides ago, that shows the clear presence of some contaminants. So supernovae that kind of sneak into our Hubble diagram, but they're actually not type 1As. And yeah, this kind of comparison really gave us the confidence that we really understand the astrophysics of the transients in supernova universe, but we also really understand what sorts of selection effects DES is introducing in our sample, and we can fully reproduce it in a simulated sample. These simulations were then used for this very critical step in our analysis, which was training the machine learning classifiers that needed to tell us what is likely a 1A and what is not.
You said that you didn't kind of tweak the model to better fit the data. Do you mean by that statement that you were blind, like you weren't looking at the data at all and you were building the model?
So we didn't really blinded anything for building the simulations, but the assumptions we made to build the simulations are all coming from the literature. So someone before us measure properties and rates of supernovae 1A core collapse. We use a galaxy catalog from DES, including all galaxies regardless of whether they were hosting or not a supernova 1A, just to reproduce a kind of a complete galaxy set of galaxies between redshift 0 and 1, which is what DES is probing. At no point we needed to change measurements done in the literature to kind of make this agreement look good. Okay, so these simulations, we're used to kind of train machine learning classifiers. So in this slide, we put an example of one of the classifiers, one of the 3 classifiers we used in our analysis, called Supernova, developed by Anaïs Muller. And for example, this classifier purely uses the shape of the light curves, and as the light curves kind of is followed up, the classifier can determine how likely this supernova is to be a 1A or not, which is what you see in the bottom panel of this plot. And so the only information the classifier gets are basically fluxes as a function of time. These fluxes are also normalized, and their uncertainty is normalized. So we don't know, the classifier doesn't know about the relative brightness between a supernova and another, and doesn't know about the relative signal to noise between a supernova and another. So the classifier cannot learn based on the information of how bright is this supernova compared to the bulk of the population. Is it significantly fainter? Then probably it's not a 1A. That wouldn't be that is an information that we don't want the classifier to learn, because that's where some cosmological information is embedded. Now, for this analysis, we use 3 different classifiers developed by 3 completely independent teams, one led by Anaïs Muller, one led by Helen Q, and one led by Yves Kollaks. And these 3 teams developed independent algorithms with slightly independent machine learning techniques. And what we found training and testing these classifiers on our simulations is that they perform remarkably well. Like, these 3 classifiers produce Hubble diagrams that are contaminated at most at the level of 1 to 2%. Now, 1 to 2% is a very small number, but easy enough for high precision cosmology, because here we're really trying to beat down systematics as much as we can. And this is for sure was for sure at the beginning one of the scariest sources of systematics. So here again, I show on a test we made on simulations where we compare the perfect simulation with only 1As and the simulations when we include our contaminants. And this is what our classifiers and our cosmological pipeline gives us, the agreement, both in the WCDM model on the left and the W0 WCDM model on the right. We recover almost perfectly the true contours. But again, to convince ourselves even more, we did this test not only in simulations, but on data. What if we use these independent classifiers on the data? Do we get different answers? And the answer is, again, the kind of shifting contours we see when we use these independent tools are significantly smaller than the statistical uncertainties.
Okay, so what you're seeing again here on the top is the residuals to our best fit cosmology in the Hubble diagram. And you can see the scatter in the data points. You can also see a yellow shaded region, and this shaded region describes the 10% of unexplained scatter that we observed in our data set, and has been observed for, since type 1a supernovae have been used using the trip equation, which we described before, our way of standardizing supernovae using colors and stretches and so on. This is saying that basically the standardization process that we've employed, correcting for the color of the supernova, the stretch of the supernova, its host galaxy environment properties, is not a perfect standardization, and nor would we really expect it to be. That's quite a simplistic empirical model, but it does quite well. It gets down to about 10% unexplained scatter, but we still have to be able to model this residual scatter and its potential evolution with redshift. Anything evolving with redshift can cause a signal that would look like different dark energy that we would care about understanding. So we model that in two key ways, using intrinsic scatter of extrinsic origin, perhaps not the best way of wording that, but we model the scatter in terms of its extrinsic origin. So in this case, modeling the properties of dust that could be intervening the supernova and its line of sight to us, or in the environment of the galaxy in the case of attenuation. And we also model intrinsic origin of unexplained scatter, this being the physical situation of the supernova progenitor scenario itself, which I'll describe in a second. So when it comes to extrinsic origin, we model the host galaxy properties and constrain the impact of cosmic dust and its dependence on the host galaxy properties. What we find is that we can constrain with the supernova itself on a population level, so not on an individual supernova level, but as a whole, differing dust properties as a function of different host galaxy properties. And this allows us to take a step forward in constraints on the impact of dust and reducing its systematic uncertainty impact in the final analysis. So we marginalize over different models of dust and the supernova's ability to constrain it on a population level. On the other hand, when it comes to scatter of intrinsic origin, we want to model correlations between host galaxy properties and theoretical models for the progenitor scenarios. So it is believed that the supernova age could be correlated with the stellar population, which we can constrain from the photometric data itself. So we have young and old stellar populations in which we model in simulations, and again can constrain on a population level from our data set. And we marginalize over a number of different tracers of the stellar populations and propagate that into our uncertainties. So this is all thanks to a rather large team. Perhaps not everyone is included here, but the key players really spent a lot of time here. Brody, Phil, Rebecca, and Lisa to dig in onto this, being one of our largest sources of systematic uncertainty. Now, rapid fire through a number of other key aspects that we've taken a step forward in terms of systematic uncertainty. Georgie Taylor has improved our light curve model. So this is the spectral model that allows us to simulate light curves. And that spectral model is called SALT, and its latest iteration is called SALT 3. Georgie improved the training data set by a factor of 1.5. And this is important because it allows us to constrain the spectral model even redder, so to redder wavelengths at better quality. And this is important because DES has a lot of high quality, very red data thanks to its deep depleted CCDs and its very high redshift data set, thanks to the fact that we're using photometric classification as our way of putting supernovae onto the Hubble diagram. And then lastly, and perhaps most importantly, is we've now taken the uncertainties in the calibration of all the supernovae that went into the SALT training and simultaneously incorporated that uncertainty in the SALT training and in the fitting of the light curves itself. So it's an important sort of bookkeeping process to vary these calibration uncertainties and their covariances amongst the different surveys that go into the training of the model and they get used in the analysis itself. And this is an important step to getting the most robust systematic uncertainties out of this spectral model.
You say SALT trained on larger 1.5 times. What is the data that it is being trained on?
Yes, excellent question. So it's largely low redshift data because we need high quality, high signal to noise data with also lots of high quality spectral observations that have been taken simultaneously. So Georgie included the Dark Energy Survey preliminary analysis from 2018. That's mostly at lower redshift and with simultaneous spectra. That's not what we did in this 5-year analysis, but it's important to include those kinds of data sets. The reality is that we needed to include a number of heterogeneous data sets to go into this training of the SALT-3 model because we need to look back many years and similarly to how we've had to compile the low redshift sample that we use when we constrain cosmology. One of the big steps forward that could happen prior to LSST or when LSST comes online is to sort of replace that whole training set with even better. But for the moment, we've done our best to characterize the uncertainties that go into that. Patrick Armstrong and Ryan Camilleri have taken steps forward on validating our analysis pipeline and simulations, many thousands of simulations of our data set to, number one, characterize any dependence on the assumption of a cosmology in our simulations. We simulate our data set. That means we have to assume a cosmology in that simulation. Ryan varies that cosmology, sees how that propagates through to our final uncertainties, and find it's a very weak dependence. So thumbs up on that. And then on the other hand, Patrick has done a brute force Niemann confidence interval validation of the extremes of the contour that we're providing so that if you want to, for example, test some kind of tension between us and some other data set, we believe we trust our contours that are coming out of our pipeline. We've been able to do it for one set of brute force validations, and now on the real data set, we believe it's consistent. And lastly, as we alluded to earlier in our conversation, we've done a deep dive on associating the supernovae with the host galaxies. This is a new challenge when you have a photometric data set. You don't have a spectroscopic confirmation of the supernova itself. You don't know the exact redshift of the supernova to within 0.01 in redshift. So that means you have to associate it with some host using some algorithms. Helen Chu marginalizes over those algorithms the assumptions in the simulations that go into training those algorithms and find that it's less than 10% of the total error budget. So at the moment, not a limiting systematic uncertainty, albeit for the future, as you go to higher and higher redshift, this problem gets worse if your seeing of your telescope doesn't get better.
Okay, so on to the results. So after all this effort, we have our Hubble diagram, and we combined it with 3 different probes. Firstly, we took baryon acoustic oscillations from SDSS, so the compilation of the most recent compilation of all of those. We took cosmic microwave background data from Planck, and we took what's known as the 2x3 point correlation from the Dark Energy Survey. So for those who aren't familiar with what this last one is, it's you correlate the positions of galaxies with the shapes of the galaxies behind from lensing, and you correlate the shapes together as well. So you correlate the positions with the positions, you correlate the positions with the shapes, and you correlate the shapes with the shapes. And those are 3 2-point correlations, all combined and simultaneously fit. And so that has awesome cosmological information in it. And we also, as a small detail, we did check that the results from all of these are sufficiently consistent that you can combine them using the suspiciousness statistic. And so straight to the results. So here is the first model that we tested, the flat lambda CDM. So in this one, the universe is flat. The dark energy is a cosmological constant. And so the only free parameter that we have in our model is the matter density. And from the supernovae alone, we find that the matter density is about 0.35. When we combine this with CMB, it gets pulled lower, closer to 0.3, so 0.315. And at the bottom, you can see the residuals where we have the offset from the best fit flat WCDM model, which is where we allow the equation of state to have a value that's different from -1. And so here you see how the different models that are the best fit here differ from that best fit alongside our data. This is like the simplest sort of visualization of our data. I said that we did use more probes than that. And so here's the slightly more complicated version with a few more curves on the plot. And you can see the combination from supernovae alone. The blue is once you combine the supernovae and CMB together. The yellow is when you have the supernovae plus the baryon acoustic oscillations plus the 3x2 point. So that one's independent of the CMB. And the redder color is when you put everything together. And so that's the most constraining result.
This residual plot at low redshifts, it looks like the blue line is a good fit. It doesn't look like the red line would be a good fit. But I guess you said you did your due diligence with suspiciousness between the additional data sets and the supernova. But it does look like these additional data sets have pulled you into a region that the supernova themselves don't actually like at the low redshift, the residuals. But I don't know. I'm doing chi-squared by I, which is, of course, always notoriously dangerous.
The one thing that we haven't shown here is the covariance matrix. So, right, the quoted numbers in the paper would probably be best to give you the intuition of how significant that is. Yeah.
Another thing that you might notice is that the red curve is to the left of all the other curves. So when you combine the data, why does the combined contour shift left compared to the rest? That's a question that often pops up. So what's going on here? And you can see that from this plot here. This is now the lambda CDM. So we've released the constraint of flatness. We're allowed curvature to change. And you can see the supernovae in blue are very complementary to the cosmic microwave background as the black dashed line. And the combined constraints are the ones that are zoomed in there. So what you can see is the flat universe is the diagonal line that is the solid line that goes through there. And it just so happens that where these contours cross is up to the top left of this diagram on that flat line. So the best fit value of the blue contour is where it crosses that flat universe is on the right-hand side, and the best fit of the CMB is a bit on that right-hand side as well. And similarly with the BAO, which is the combination that's in orange. And so it's when you put all of those together, where the X marks the spot goes, where all those contours cross, is to the top left in the flat universe. And so that's why in this previous plot, the dark orange contour is to the left of all the others. For lambda CDM, one of the important things is that the best fit constraints are bang on the flat universe. We see no evidence that they're for any curvature when you combine all this data. Now, when we have a look at the flat WCDM, so this is where we've allowed the equation of state of dark energy to be other than -1. It's still a constant, but something that's not -1. It's a bit of a contrived model, but it's one of the ones that's very popular to test in the literature. These are the constraints that we get. And interestingly, you'll see that our best fit contour is above the -1 line for the most part. And where it crosses the cosmic microwave background, which is the dashed line, and the combination with the BAO and 3.3/2 point are all slightly above that -1 line. And so that means our best fit isn't exactly a cosmological constant. That would be a W equals -1 best fit. And so this is our first hint that we're finding something that's not quite the standard cosmology. And finally, we tested a model in which the equation of state of dark energy can vary with time. And for this one, you have two parameters, the constant part, which is W naught, and that would be the bit that should be -1 in the standard model. and WA, which is the part that varies with scale factor, and that should be 0 in the standard model. So anything with WA that's not 0 indicates some sort of time varying dark energy. And here you can see all of the parameters fit simultaneously. So you've got W0 and WA on the vertical axes, and you've got omega M and W0 on the horizontal axes there. So you can see all of the different combinations. Now, zooming in on just the W0 WA part, which is up on the right, is showing one of the more interesting results. So the crosshairs are where the standard model would be, and we're finding answers to the bottom right of that. And this is our indication that their dark energy might be varying with time. So the WA parameter on the left, you can see on the plot with 3 panels that we let WA go really negative. We went as far as it needed to go to fit all of the data. And so our best fit WA is actually around -8, and that with large error bars. But we're finding there some strong evidence, well, not strong evidence, let me rephrase that. We're finding some evidence that there might be time variation. But as you can see, the error bars are still big. So we need more data to have confidence in this before we're claiming that dark energy is definitely varying with time. Now, when you combine with the other data sets, you see that the error bars get smaller, but they're bumping up against that WA of 0 line still. So there's only slight evidence that we're finding a time varying equation of state. And this is what the residuals look like for the best fit flat W0 WA CDM. That's the blue line there. You can see, because you're allowed to have time varying dark energy, you can get a few more wiggles in there. And we were interested to see whether there's any particular part of the curve that's like driving that fit or anything like this. And it turns out that even that point up near redshift 1, even if you drop that high redshift point, it's not really driving this shape. Indeed, we ended up, you get quite consistent results even if you drop those high and low redshift points. So these are really confusing plots, which are in the appendix of the paper. And what basically you're seeing is what happens if you drop the high or low redshift points from the fit.
What is the definition of high and low here?
So the high redshift is anything above redshift 0.85. So if you remember our earlier plots, it's the one where we only have 2 bands for most of our light curves. And the low redshift is dropping all of the external samples. So getting rid of any samples that aren't the dark energy survey. So this, on the right, you see the W omega M. So this is the WCDM plot. And there you can see there's this big degeneracy banana for supernovae. And if you see shifts along that degeneracy banana, you're not too worried, because when you combine with cosmic microwave background and stuff, the where they meet doesn't change very much. And so we see shifts along that degeneracy direction. When we did some tests, there's slightly larger shifts than you would expect from just statistical fluctuations in the data set. But that's exactly the kind of thing that you would get if your model isn't adequate to fit the data.
So this top right one is not including WA.
That's correct.
So yeah, so that could be evidence of WA, right? Like that if you remove the low redshift stuff with the high redshift, the WA is exactly saying things are changing with redshift. So okay, that makes sense.
Yeah. So the fact that this shifts itself could be evidence that we do need the more complicated model. We're always concerned that there's, some systematics that we haven't identified at one end or another. So we search for those kinds of things. And one of the things that will greatly reassure everyone, I think, is when we have a brand new low redshift sample that can completely replace the old one. So there's work that Dillon's doing, and he can speak to as well about, and many others about, improving that low redshift sample and getting data on the same telescope. So we have extended redshift range that's all with the same calibration, and there's no extra uncertainties there. So interestingly, when you have the W0 WA plot and you cut one end or the other of the redshift range, the central best fit doesn't really change that much. So it's sort of stable in W0 WA, but you see that it shifts a bit in the W and omega M. Again, mostly along the degeneracy direction. But
another way of phrasing this is that it's not one of the samples, the low redshift or high redshift sample, that's driving the significance of WA that we see.
Yeah, so one of our big questions then at the end of our paper, we went through a series of big questions, and one is the dark energy a cosmological constant? And of course, we went and did model selection statistics to see whether there is a preference for one or the other of these models that we tested. And you do find that there is a slight preference for flat W0 WA CDM, even after you've taken into account all of the extra parameters that it introduces for the supernovae alone. So the blue dots, the sort of aqua dots, the supernova alone data. That preference gets weaker once you combine with the other data sets, and the error bars shrink. So, but one thing that's definitely not preferred is any curvature. So there's no hint that curvature is required. But this data alone is still inconclusive as to which model is the better fit, because we know if you have a more complex model, you're going to get a better chi-squared, you're going to get a better fit to the data. And so that this tries to take that into account. But that makes it even sort of more exciting what came out then after our data, which was a few months later. The Dark Energy Spectroscopic Instrument, DESI, using baryon acoustic oscillations, also found a preference for a negative WA, so some sort of time variation. So we just put their plot here as well. And the black dashed line is the baryon acoustic oscillations alone that are also preferring that bottom right quadrant. Now, Maria kindly reproduced our plot on the same axis, so we're the same scale. So you can see we're in the same direction. Maybe not as positive a W0 or as like far from -1. The result that DESI produced, once you combined their data with ours, found that there was a greater than 3 sigma evidence that WA was less than 1, which, is less than 0. So that's quite interesting.
It's interesting that all the three kind of pieces, the supernovae, the BAO, and the CMB are all kind of independently slightly favoring that bottom right-hand quadrant. And so, of course, when you combine all three, they more significantly favor it.
To the big questions, what is the take-home message here? So firstly, is the expansion of the universe accelerating? This is what supernovae are famous for having measured first, and the conclusive answer here is absolutely yes. So it's actually a relatively subtle question to quantify, and which is why I put this whole pile of text here. But in the lambda CDM model, we are very, very confident that the universe is accelerating, and even more confident that it was accelerating in the past, because our measurements are in the past, they're further away. And if you assume flatness, there's basically just no likelihood left that the deceleration parameter could be actually decelerating. So there's just, it's very, very conclusive that the universe is accelerating. The next big question that we've already addressed was, is dark energy a cosmological constant, or maybe? And we see evidence for something that is not a cosmological constant. And we also agree in this sense with another a set of data from supernovae that came out just before ours, which is the Union 3 results. And so here is the contours that they found in the W omega M plane, and you can see they also prefer a W that's greater than -1. So if you overplot our contours on top of theirs, you can see that we're actually in really beautiful agreement. So this data set is one in which all the high redshift supernovae are independent. They're a completely different data set. They used a completely different technique as well to analyze this data. They used a Bayesian hierarchical model. And so the fact that these are in agreement. There is a slight overlap. There's about 194 supernovae at low redshift, which are in common to the two samples, because we still both have some, there's just not enough low redshift supernovae known to get rid of all of them. But apart from that, the data and analysis are completely separate. And so the fact that they're in agreement, I think, is really strong, sort of like reassuring that the analyses that can be so different can still agree.
So, in talking about whether dark energy is a cosmological constant or not, we couldn't help but bringing up the famous DESI plot that that combined DESI BA results from the year 1 DESI data, CMB measurements, and 3 different supernova samples. And after this talk on the DES supernova 5-year results, people will be able to understand a bit better the differences between the 3 different supernova samples and analysis. And so I like to show this in a kind of this 2x2 grid, where we show that the main differences are driven by the fact that 2 of these 3 analyses were using spectroscopic supernova 1A sample. So they were using spectroscopically confirmed 1As, and DES was just using a photometric supernova 1A sample. While Pantheon Plus and DES 5-year share the same method for correcting and modeling selection effects, which is a simulation-based methods, and that's why we spend a lot of time telling you about how we build our simulation. While the Union 3 sample was analyzed with this method called Unity, that is essentially a Bayesian hierarchical method that has less emphasis on these simulations and reproducing selection effects. So these are kind of similarities and differences between these 3 supernova analyses that have been featured in the DESI results. And that, despite some substantial differences, kind of give us this super interesting result.
If the high redshift supernovae are all essentially different, what is the difficulty of combining these data sets into one big supernova? I mean, maybe Pantheon Plus and Union 3 aren't different, but if the DES 5-year are different, why can't we combine them and get a combined supernova constraint plot here? Like DES BAO plus CMB plus Pantheon plus Union 3 plus DES Year 5.
We would love to do that. It's still non-trivial. There's still some overlap. For example, the 3-year data set of the Dark Energy Survey is actually within Pantheon Plus. Also, there's a little bit of shared low redshift supernovae again. But actually, the most important thing is that when we do the analysis pipelines in the simulation-based methods, we want to propagate all the systematic uncertainties that are actually shared between Pantheon Plus and DES 5-year, because we're using the same or similar SALT spectral light curve models, covariances amongst the calibrations, and so on. And you need to propagate that from end to end through the whole pipeline to characterize the covariance between all of the different supernovae. So if you were to just take the DES 5-year data set and covariance and the Pantheon Plus 5-year data set and covariance and add them together, that wouldn't give you the covariance between the two. So a little bit more subtle. It's certainly an effort that people are considering undertaking, but there's also some more exciting data sets already in hand and on the horizon that maybe it would make sense to incorporate those, which also improve on some of the robustness tests that we've sort of set as our metrics.
Other than the LSST dataset, which maybe is 5 or so years from now, what other ones did you have in mind when you said that?
Well, okay, so in terms of LSST, the first year of LSST will already dwarf the Dark Energy Survey dataset. So now that might be a few years beyond 1 year of collecting the data, so that isn't on the immediate horizon. But there's other data sets in hand. We stopped taking the Dark Energy Survey data in 2018. Since then, we've been collecting data on the Dark Energy camera, that same camera, on the Pan-STARRS camera, which is one of the other main supernova surveys. There's ZTF that's going on right now. And so that data is being analyzed as we speak. And that's really well-calibrated, well-understood selection effect data that we would like to incorporate. But that's probably worth another talk in itself. So.
Okay, and what's the time frame to expect like such a paper emerging?
As soon as possible, and who knows?
Less than 3 years?
Well, definitely the goal is to have something out before LSST's, is stealing all the human power away, because it's also, once it becomes the most exciting thing, we would like to have whatever this final last hurrah is before LSST.
Yeah, and the emphasis for the Dark Energy Survey and all of our analysis was to keep the systematics as clean as possible. So we only wanted to use the best data. So it's sort of, once you've got Planck, we weren't using WMAP anymore. It's not quite a perfect analogy, but we wanted to have the strongest, least out of our systematics possible. And so sometimes it's better to just use the really polished data. The next big question was, how old is the universe? Well, the answer is if our best fits are true, then it's slightly younger than we thought. So this is just that plot of scale factor versus time in the different best fit models. So if you have the if you just have the supernova data, then the W0 WA model, you actually get quite a bit younger than the standard model, and so much so that would probably be a problem with the age of the oldest globular clusters. So we don't think that it should be as negative as our best fit finds, but the error bars on that, as you know, were really large. So when you combine all the data, you just get a slightly younger universe for the best fits of the combined data. And the final big question is, does our best fit resolve the Hubble tension? The answer is no. We don't actually have anything to say here on the Hubble tension because we're not calibrating our supernovae absolutely. We're just doing the relative brightness, and we've only contributed high redshift supernovae that don't help with the H0 question, which is the low redshift measurement. So there are some models that would reconcile or sort of reconcile the CMB measurements with the low redshift measurements. But the most simple ones that would do that have an equation of state in the WCDM model that would be less than -1, and we find the opposite. So it's unlikely to help with the H0 tension.
So you actually make the Hubble tension worse for those models?
For those models, I guess, yes. And so that brings us to the end of our cosmology stuff for today. But we've done a whole bunch more with the data set. You can do a whole bunch of other cool, interesting stuff with the DES supernova data beyond just fitting a Hubble diagram. And so in other things that we've had a look at, Paul Shah's looked at supernova lensing. So you get lensing magnification due to the structures along the line of sight, and you can use supernovae as point sources in the background to detect the structures in the foreground. And so we're going to also have another video on that. We've tested a whole bunch of models going beyond just the W0 WA parameterization, and so having a look at different, sometimes more physically motivated models. And Ryan Camilleri's had a look at that. And Ryan's also done the inverse distance ladder, where instead of where we do try and constrain the absolute magnitude of the supernovae, but not anchored to low redshift measurements like Cepheids and tip of the red giant branch and that sort of thing, but anchored instead to high redshift, where you anchor them to the baryon acoustic oscillation scale and see what H0 that you get. And as a final fun one that I really like, we've also measured time dilation. So we expect that because these galaxies are receding from us and going away, you expect that their light curves for supernovae should be wider by a factor of 1 + Z, which we see coming out beautifully.
One of the things that I would normally have asked at this point, I think, which would have been super interesting, is what models beyond W0 and WA might fit this data. However, I guess that is exactly what this talk by Ryan Camilleri will be.
Yeah, so there's a whole bunch of different models that go from everything from just different parameterizations of W0 WA, models that try and couple dark energy and dark matter, to models that try and look at back reaction and whether there's any reason that our homogeneous assumptions are failing. But I think one of the things that the field really needs, what it feels like to me, is that we still are waiting for that aha moment where we have a model that is like, yes, this feels like obviously what dark energy should be, and explains all of the problems with, if vacuum energy has a problem with how much of it there is in the universe compared to quantum physics predictions. And I feel like the next breakthrough might have to be a theoretical one, where we really have something new, because from my perspective at least, nothing massively compelling has come up to explain dark energy, even after all these years.
Yeah, and you mean literally if it's a cosmological constant, even like it, yeah, it's just one term you can add to your equations, but why that magnitude has all sorts of like concerns, I suppose. Yeah. And so now if we're also getting to the point where there's Hubble tensions, S8 tensions, W0, WA tensions, I don't know, it's not a tension, I guess, because it fits the data quite well, but tensions with the theoretical, the W0, WA model is not necessarily a model that fundamental physics likes much. So I guess there's a tension there between fundamental theoretical physics and what the data is asking us to do.
And that's why all of our data is public. So anybody who has their own favorite model can use it. So we've put the link to the archive of the paper here, where you can go and you can click on the GitHub link, and the data's all going to be in Zenodo. And we're going to have some tutorials to walk people through how to use the data, how to download the data. And so we are really enthusiastic to see people do stuff with our data that we never thought of.
Cool. Well, that very, very interesting stuff. And yeah, looking forward to seeing where people go with the data once they start using it. Last bonus question. What work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the rest of the community?
For me, I think one thing I'm super excited about is actually gravitational waves. I don't think this is underappreciated by the community, though, because I think there's a lot of hype about gravitational waves. But using those as standard sirens to measure cosmology, I think has a huge amount of potential in the next couple of decades.
I guess I could say one underappreciated area within the context of supernova cosmology is measuring the velocity field from the supernovae themselves. So this is not something we could do with DES, but in the era of all sky surveys like LSST, that will collect a lot of low redshift supernovae. This is where we can best constrain the velocity field at low redshift. You can actually use the supernovae themselves to constrain what component of the redshift is from cosmological expansion and what component is from the peculiar motion due to the poles of the matter field itself. And it's an excellent probe to cross-check other measurements like redshift space distortions or lensing when it comes to understanding things like the S8 question.
In this era of high precision cosmology, having completely independent way of measuring these like super important cosmological quantities is very critical. And so, for example, the fact that supernova with LSST for the first time in basically the history of supernova cosmology will allow this completely independent measurement of sigma 8 is something that is maybe not appreciated from the wider non-supernova 1A cosmology community, but within the supernova 1A cosmology community is becoming very kind of intriguing perspective.
Yeah, indeed. I think that's a really interesting aspect of things, because the low redshift universe is the one that all of the light that we ever see has to travel through the nearby universe to get to us. And so any inhomogeneities or unexpected things in that low redshift universe could affect our cosmological measurements. So making a fantastic map of the nearby universe is something I'm also excited about.
Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos. Click like to help with YouTube algorithms, both for the channel and for you, because YouTube will know to recommend more stuff like this. And share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, check out, if you're watching this more than a couple of days after it was released, check out some of these other Dark Energy Survey talks. And thanks, Dylan, Maria, and Tamara for the great talk.